Good morning to all. I hope I am audible to all.
Yes, sir.
Welcome to fourth day of Faculty Development Program on Data Sciences Advanced Level. Today we have a eminent speaker, Dr. Mohammed Sohail sir, the Technical Manager, Artificial Intelligence, SCGB Bangalore. Uh, so sir will handle today fully 3 sessions. So I will invite Dr. Manas Rahman, Research Scholar, Department of Computer Science, to introduce the research person. Manas, please.
So thank you, sir. Sir, am I audible?
Yes, it's audible, clear.
Okay. So good morning to one and all. So it gives me immense pleasure to introduce our resource person today, Dr. Muhammad Suhail. Dr. Suhail is working as a technical manager at Standard Chartered Global Business Services Private Limited, Bengaluru. His research and development interests include artificial intelligence, machine learning, deep learning, computer vision, and natural language processing. He has more than 20 research articles into his credit, published by international journals and conferences of repute. His publications have obtained around 300 citations from contemporary researchers with H index 7. He has been actively connected with academia due to his passion towards teaching and research. He enjoys delivering technical lectures and giving hands-on training on the applications of AI. So without any further delay, I would like to invite Dr. Muhammad Suhail sir to proceed with the session. Sir, please.
Um, Thank you so much, Rahman, for the nice introduction. So, good morning, dear participants. Yes, I'm indeed very happy to be a part of this, reputed program, the Faculty Development Program conducted by the Central University of Kerala. So, I've been involved with the Central University of Kerala for the past couple of years uh, in such a programs, and I see that especially Professor Kumar, Professor Rajesh, Professor Taslima, they are very much enthusiastic in conducting such programs by having a lot of eminent researchers and speakers across the globe. In fact, so a lot of appreciation goes to them for conducting such an event. So there is a lot of people can gather together and exchange their knowledge and ideas. So I wish all of you are enjoying the sessions and also gaining a lot of information. Uh, with that, you can definitely make some fruitful efforts later in your academic journey, and internally your students will also be benefited going forward from this. So with that, let me share my screen so that we'll start with our session. So let me know if you all can see my screen.
Yes, sir, visible.
Yes. Right. So the today's agenda is around the neural networks and deep learning. So as I went through the sessions that were planned and have been covered, so I understand that um, it is into the the machine learning and the statistics and mathematics part of it so far, and as a continuity to them, um, the evolved, very well evolved, and the present, you know, a hot topic, that's deep learning. So, uh, it's definitely not completely different from what you have understood so far, but only the way in which your machine learning happens. So it is also a branch of machine learning. Okay. So it's a special type of algorithm which has seen and gained a lot of importance due to its enormous success. Let's get into the intricacies of it with different applications, mostly focusing on to the computer vision. Okay, so we'll be covering the introduction to neural networks, which is the backbone of any deep learning based architecture. Then we'll understand how and why it is called as deep learning, and let's dig into the math and science of the deep learning, focusing on to the convolution neural networks, and we'll go over some of the very well known and accomplished CNN architectures. Then I'll take you through some of the interesting applications, and finally a uh, demo wherein I'll walk you through the code of how to implement such a deep neural network architecture. Okay, so in today's 3 sessions, I'll be covering these in detail. So I also expect interactions from you all, so that the session will be very much interactive, and at the same time all of you can be benefited, and also I can also be benefited with your ideas and you know uh, the kind of approach that you take, right? So let me begin with a brief history of neural networks. So it began in the early 1940s. So the very first neural network concept came into picture, though it is uh, popularized in the late 1980s because of essentially because of the computational burden that it requires. So it was not so popular between these two period, because as you are well aware, the computation or the compute power was not so great in such a time period, right? So this was a result of the discovery of new techniques and developments and general advances in computer hardware technology, as I said. And some of the neural network models are, you know, they are the models of biological neural networks. If you just recollect, our brain is called as a neural architecture. Uh, and that is how the neural networks are also evolved. Historically, much of the inspiration for the field of neural networks came from the desire to produce artificial systems capable of sophisticated and intelligent computation similar to those that the human brain does, and possibly to enhance our understanding of human brain. So, so far you may have come across a lot of machine learning techniques. None of them are very close to the way we work, the way the human brain works. So the human brain works in a very different, way, wherein you will see that it adapts to the environment, it learns a lot of other things, and the way it represents the information is completely different from what we have understood in other machine learning techniques. So that is where the neural network concepts and the, the inspiration has come to come up with a technique which is more closer to the way human brain works. And most of the neural networks have some sort of training rule. In other words, you can also say that neural networks learn from examples. Like you show children different instances, say for example dogs. So you go on showing the dogs to the child and say that, hey, see, this is a dog. And every time you show a dog, it's a different dog probably, or a different scene or a scenario in which the dog has been presented to the child. And the child will gradually adopt and learn not to remember a particular dog, whereas it tries to understand and represent a, the the animal called dog in his brain, at a very high level of generalization, so that whenever you present him or her a new dog, dog's instance, for example, so she'll be still capable of saying that it is dog, even though she has not seen that dog before. This is the very first time, but her representation of dog in her mind is so generalized that she can now map it to any dog instance which she come across in her uh, you know later days after having understood the concept of dog. So in a similar fashion, we want the neural network, or the neural networks have been built in such a way that you go on presenting examples, right? Or you can call it as samples of the uh, the pattern, basically whatever object that you want the network to learn and represent. You go on presenting many examples of it, okay, with varying say for example, if it is a kind of dog, if I say, you go on presenting the dogs, say in the format of an image. You go on presenting the dog's image with various poses and various species of dog and in various conditions, right? In various conditions, when I say, maybe the scene conditions or the lighting conditions, or so whatever differences that you can make out, you go on presenting the samples of it, and see that your network tries to map all of those dogs images into one group called as, or into one concept. You can now generalize it to a concept of dog, or a pattern of dog, at a very highest possible generalization level. So that is the expectation out of the neural network. So neural computing must not be considered as a competitor to the conventional, or you can rather say the other types of machine learning techniques. Rather, it is a complementary. So sometimes you can always uh, cannot say that neural networks or deep learning is possible for any type of examples, or it works best for all type of problems. No, it's not possible, or at least there could be some problems which may not require deep learning, or may not be possible with deep learning, but very much possible with other types of machine learning techniques. So but just that in today's world it is been dominated because of its success, and it has its own requirements. If you meet such requirements, then only it is possible for you to use deep learning, deep neural networks in your problems. Okay, I think you will be learning it better as we go through in our sessions. Okay, so with that background, if you try to raise a question of what are artificial neural networks, then so artificial neural networks are the models of the brain and nervous system. So how your nervous system and brain are connected to form a network to achieve your every activity that you perform. And they are highly parallel in the sense that they process information much more like a brain than a serial computer. That means the information processing is distributed and the processing happens in a parallel manner. And learning is a very special thing here. So learning will be through a lot of examples, and it learns with very simple principles. It is built with very simple principles, but it can achieve a lot of complex behaviors. Okay. So if you try to compare neural networks uh, versus conventional computing techniques like conventional machine learning techniques, so the conventional approaches mostly are mostly will be using deductive reasoning, meaning that you apply known rules. Say for example, in the case of nearest neighbor, you want to decide a sample, the class of a sample, by just estimating the distance of that sample, in a Euclidean space. You try to compute the distance of the given sample with those that are present in your training set, and whichever is very closer, and you see that maybe because of the k factor, you decide one of the classes to which this sample is very close. So that is the rule that you have kept for the classification, for example. So whereas here in the case of neural networks, it is inductive reasoning. That means you give the inputs and outputs, and the rules will be constructed by the network. So you do not create rules. Instead, the rules, or you do not impose a rule. The rules will get created by seeing or by looking at what is the input and what is the output expected. Okay. And computation is centralized, synchronous, and serial to the rule, whereas here the computation is collective, asynchronous, and parallel. Means asynchronous means multiple computations will happen without any dependency with other computations, and they'll happen in parallel mode, all collectively. So in conventional memory is packeted, literally stored and locatable, uh, and addressable, whereas here the memory is distributed, meaning the memory or the information about the data is not at a single place, but it is distributed all across the network, and it is internalized, short term, content addressable. Short term in the sense, whenever you pose and give newer samples, the older memory will be losing its importance, and the newer information will be replaced by the older one. The conventional approaches are not so fault tolerant, uh, meaning that it is in terms of the way that it is used. If it is built with transistors, like if one transistor goes down, then the entire approach, entire network will fail. Whereas here it is fault tolerant, meaning that it is not dependent on a specific part of the network. So even if one part, something like even if one limb of a person is down, the person is still able to perform his activities. He'll still be the same effective person as he was before. So such a kind of fault tolerance is available. Okay, so it looks for the exact match, whereas it is kind of inexact. You have a static way of connections. Here, dynamically the connections get updated. Okay. So you go for conventional approaches whenever you think the rules you have are very much defined for the input data in your hand, and whenever you cannot define such rules and it is complicated, then you can go for neural networks. Okay. So with those high level differences, if you try to look at the applications of neural network, uh, I've just tried to keep a couple of applications here, but today you can see enormous number of applications, um, you know, for coming out of the neural networks or deep learning. Say in classification, you can think of a marketing application, something like you want to know the pattern of spending of a consumer. So the marketing, say the retail business, they want to know uh, what is the most you know spending item that the consumer goes for. Based on that, he can decide what should be the next item that should be put in his stock, so that it will be useful for the consumer, and consumer will buy it, and internally he'll be benefited. So in defense, for example, the radar and sonar image classification in agricultural fishing, you can see the grading of the agricultural products. In the health sector, you can see a lot of applications like ultrasound, ECG, image classification, EEGs, medical diagnosis today, which is gaining a lot of importance, and there are enormous success at the same time. And if you look into the recognition and identification related applications, so in general, computing and telecommunications, you can look for like speech recognition, vision based applications, and handwriting recognition applications. In finance, you might see signature verification, banknote verification. In assessment, like you can look for the product inspection, monitoring and control, like the automation of quality checks in the manufacturing units. In defense, you can look for the target tracking. Um, in security and defense, so motion detection, surveillance, right? So all these are now the applications of neural networks. Yes, there are also the applications of other machine learning techniques, but specifically in deep learning, there is a lot of success that we have seen today. So as I told that it is the inspiration that was taken from the biological neural networks. So it is definitely good to spend some time to understand how the biological neural network works, at least from the layman's perspective. So if a biological neuron is visualized, this is how it looks like. And a brain is a collection of about 10 billion interconnected neurons. So this is just one neuron. Such, more than 10 billion interconnected neurons are present in human brain. So human brain is a very complicated system, but made up of such small, simple, and easy units which are connected to achieve a very complicated task that we are working with. So if you try to understand a simple neuron, it is a cell that uses biochemical reactions. So we do not have any computation like a digital computation that is happening in our brain, whereas it is a biochemical reaction, and there will be some electromagnetic uh, you know effect as well that the brain goes through. So these biochemical reactions will receive, process and transmit the information, right? Whenever you do some sensing, like you touch a object, then your the sensory organ, the touch sensory organ, will take the information all the way through your brain, and the brain will pass through that information to the neurons, and that neurons will process it and pass a processed information to the subsequent neurons. Okay, so every neuron basically does receiving of information, or you can may also call it as raw data, process it, and then transmit it. So each terminal button, so a neuron will have a lot of terminal buttons. So each terminal button is connected to other neurons with a small gap called as synapse. So if you look into the right picture, so this is the terminal button at the end of a neuron in one particular branch. So that will connect to the dendrite, which is the branches connecting to the neurons with a small gap. So this gap decides how much information should be flown from here to this. Okay. So how much information in the sense, what should be the weight or the importance of this information that is being passed from this terminal button to this neuron will be decided by this gap. If the gap is high, the importance will be less. If the gap is less, importance is high. So vice versa. So that is how the connection happens. It's not tightly connected, they are loosely connected with such gaps. Okay, nucleus is where the computation happens. Okay, so that's the essential concept. A neuron's dendritic tree is connected to 1,000 neighboring neurons, as I said, and the strength of all the received charges, or what you can call it as the inputs, are added together through the process of spatial and temporal summation. So as you can see, this neuron is not just connected to one neuron. It is connected through these branches to a lot of other neurons. So it is receiving input from thousands of other neurons, and all the inputs and each dendrite is connected with such terminal buttons with a gap, and that gap will decide the weightage of that information that is flowing through from other neuron to this neuron. So there is a information that is getting passed, and there is a weightage associated with that information. So the input or the what you can call it as the charge that is being received, and the weights will all be used for a uh, summation, or you can just call it as some computation within this nucleus. And after that computation, it you know passes the computed information to some other neurons, okay, connected through such terminal buttons. Okay, so as you can now imagine, so a neuron will be connected to lot of other neurons which are passing information to it, and it does the computation, and it passes forward some more information to some more neurons. So the number of neurons connecting to it may be in millions or billions, and the new number of neurons this gets connected maybe again in millions and billions. Okay, so that is how this structure is very complicated, but essentially the crux of it is very simple. Each neuron receives the information, processes it, forwards the information. Okay, so with that, the understanding of human brain, how the neural system works in human brain, the artificial neural networks were laid down. So ANNs incorporate the two fundamental components of the biological neural networks, that is neurons, okay, or you can also call them as nodes, right, and synapses, which are the weights. So now we bring these two concepts of human neural network, the biological neural network, to form this artificial neural network, wherein I want to have the nodes, which are neurons of the biological neural network, and the neurons should be connected to other neurons through weights, okay, which are synapses in the biological network. Okay, as you can see, each edge has a weight, and each edge is connecting two neuron. Okay, so then these two neurons are connected with this edge with some weight. So then whatever information that is passed from this neuron to this neuron will carry the weight that you associate here. Okay, fine. This is how we are trying to simplify the biological neural network with this neuron concept. So in lot of inputs are coming up to this neuron or a node, and it has some summing and squashing functionality sitting within this neuron, and which processes the information that it receives and generates a new information as a result or as an output, and it sends it across. This output may be connected to a lot of other neurons. Okay, so can you imagine this way of you know mapping between the biological neuron versus a node in artificial neural network? Okay, great. So if you further look into how this node or a neuron is working, so a structure of a node is, it is going to receive some input and it is going to produce some output. Okay, in between it has a squashing function, and that squashing function does some computation based on the input that it receives, and further it also tries to limit the output to a particular range. Okay, so do some computation and scale it up or down, or keep it in a specific range, something like 0 to 1. Okay, so bring the value to 0 to 1 and send it as output. Okay, so it has basically a summing and squashing function sitting inside the node, which is called as your neuron processing part. Okay, so if you imagine such one neuron, uh, and if you see such a collection of neurons connected to form a network, and you can imagine in the biological neural network there is no particular direction in which the information flows. It is that the neurons are connected forward and backward, and this neuron may again be passing information to this neuron. So that's the very much generic structure that biological neural network has. Whereas here, in the artificial neural network, because we want to have a specific structure wherein we want to send in some input from the external world and get some expected output, the desired outputs at one level. So we want to define two layers called as input layer and output layer. So the input layer is where the data is presented to the network, and the output layer is where the data, the outputs are generated and passed out of the network to the external world. So we want the information to be flown from the input layer all the way through the hidden layers, which are again a collection of neurons connected to the input layer, and maybe there could be several such connections. So there is an input layer, there is a hidden layer which does the computation, and there is an output layer which generates the final output. So as you can see, this is uh, this network is a kind of forwarding the information. So is this, and that is the reason why this type of network is called as feed forward neural networks, meaning that the information is processed in a particular direction from left to right, say from input layer to the output layer. So such type of neural networks are called as feed forward networks, and all the uh, neural networks that we study and use in our applications are feed forward neural networks. Okay, meaning that you'll have always an input layer and output layer defined based on your requirement and the data that you have in your hand, and then a hidden layer which does the processing. But basically every layer is composed of neurons, right? And you can see that the information is distributed. So this particular input neuron has some information which is distributed across the hidden layer, and similarly other neurons also. So the information is distributed, and information processing is parallel. So you can see that, so when this particular neuron is doing its computation, all the other neurons are not sitting idle, they are also doing their job parallelly, and hence the information processing is parallel. And at the end, this at this layer they all get accumulated and do final computation and generate the outputs. Okay, so that is the reason why neural networks are called as parallel processing systems. So when the information flow is from input layer to the output layer. Okay, so this is the very essential basic stuff, the foundations that you should be aware of, so that you can understand and digest any complicated neural network architecture uh, which is being generated or produced by the research community or by the industry. Any complex architecture is definitely built out of these foundational pieces. So if you are very good at these foundation concepts, then you can definitely understand and digest any research papers that has built a new neural network architecture. Okay, so the smallest possible neural network is called as perceptron, which is nothing but a neural network having only one neuron. Okay, a neural network composed of a single neuron is called as perceptron. So a single neuron based network can also be used in some of the applications depending on the complexity of the application. So if you can see that this is a single neuron which is accepting three inputs x1, x2, x3 with some weightages associated to each input. And what does this neuron do? It does the summation, which is essentially the dot product. So as you can see here, the summation of the dot product, or I mean, is the summation, or you can call it as a dot product. So assume this x1, x2, x3 is one vector. Okay, w1, w2, w3 is another vector. You do the dot product of these two vectors. What's the dot product of the two vectors? It is element-wise multiplication followed by summation, right? So that is what is this particular function is doing here. So you do the element wise multiplication and add up the products to get a single scalar. That's the dot product. So a neuron just does the dot product of the inputs and the weights. That is first data processing that happens in the neuron, followed by it will have a squashing function. So the squashing function tries to bring uh, the value that it generates as output in a specific range. Say, for example, you want to use this neural network for a binary classification problem, meaning that either the input that you passed should be classified as class 0 or class 1, right? Class A or class B. So you can decide whatever label that you want to give it as, like a dog or uh, you know some other like cat, or you just want to say yes or no, fine, whether it rains or not. So that's such a type of binary classification is also possible. So 0 is meaning that no and 1 meaning yes. So if you create a feature vector x1 x2 x3 and decide the weights w1 w2 w3 based on the input feature vector, say this input feature vector may be something like so you are going to decide whether it is going to rain or not. So temperature, humidity, and say maybe the season or the month. Okay, so these three are the features that you've extracted, and each feature has its own weightage based on the temperature, humidity, and the season. Uh, whether it can be chances can be it is going to rain or it's not going to rain. So if it is more closer to the raining, then definitely it produces say 1. And how can that squashing be done after the summation? You can just keep one threshold for this summation or the dot product. If the dot product that is computed for the input vector that you have presented to this perceptron, if that dot product is less than or equal to the threshold that you have set, then it is not going to rain, or otherwise it's going to rain. So I just gave you a hypothetical application, so you can map it to any such application.
Sir, may I ask you, how
Yes,
is
please.
perceptron different from Maculopat's model?
Sorry, madam. How is
How is
perceptron different from?
Maculopat's model? I see the figure is same for Maculopat's model also. So how the both models are different? What is the difference of both?
I'm
The
not getting
input,
the
weight,
last
everything.
word. Which model are you talking about?
Maculopate. Maculopate.
Yeah, maybe definitely it is inspired from the same perceptron concept, whereas this perceptron is a basic unit of neural network. Okay, and you can just say that this perceptrons, the working principle is as simple as your a simple regression problem. Okay, so you generate a regression curve based on this particular equation itself, and whatever it comes out, you keep a threshold and decide. So that's how it works. But the interesting concept is how these weights are decided. Okay, so that is where the neural network training comes into picture. I think you will understand it in a better sense as we go forward. But just understand the working principle of this perceptron. Okay. Yes,
Excuse me, sir.
what you said
One
is
question,
right.
please.
Yes, please.
Yes, sir. Thank you.
Sir, what is this threshold value? What is this threshold here?
Yeah, this threshold is like you are going to set based on your experience, or you going to decide with a lot of experiments that you do, so that this threshold is very much suitable for your application. And it is not necessary that you always should have a threshold over here. For example, a threshold could be as simple as 0.5. If the summation leads to more than 0.5, then classify it into 1. If it is less than 0.5, classify it as 0. So what you can think is it is more likely that what you generate as output here is a kind of probability. So more the value, or you reach, you convert it to 1. If value is lesser, you convert it to 0, kind of. Okay.
Okay, sir. Thank you very much, sir.
So if I try to generalize this, okay, this is how it looks like. You got a input vector and a weight vector, and this neuron has a function. Basically, this is the um, squashing function. So after summation is the standard function that happens. So after the summation, this is going to do a squashing of the summation. And the squashing, as I said here, the squashing could be just based on the threshold. You convert the some value to either 0 or 1 based on the threshold, or it could be a any function which basically takes the output to a specific range, which is meaningful for again. So this function, what you are seeing here is an example of such squashing functions. It is called as a sigmoid function. Basically, sigmoid function will take the value, whatever value that you input, okay, be it a negative value or a positive value. When you pass it to this sigmoid function, the output will range from 0 to 1. Okay, so now you can take the output of this fx, the sigmoid, as a probability, and say, for example, the probability you are going to build a network to decide the probability of say rain, or probability of say in the case of say you may be selling a product, so you want to decide whether the product gets sold or not, so you want to come out with a probability. So this 0 to 1 is the probability that it generates. So if the summation is somewhere close to say minus 2, then the probability will be here. So the probability is very less, the product gets sold, whereas if the value is going high, then the probability will move closer to 1. So, but it has a cap. It will not cross 1 for any value till positive infinity and negative infinity. It will not cross 0. So that's how any summation that is generated out of the dot product will, if you pass it to the sigmoid function, then it will come back to this range 0 to 1. So now it is like very much interpretable than having, say, if you generate a summation value or a dot product, if the dot product is something like 300, it is not meaningful, right? What is 300? Whether 300 is big or small, or it is good or bad. So you do not know. You cannot associate a decision with the value called 300. That's the dot product value, because dot product has no scale, a specific scale. The dot product is not in a specific range. So we want to bring that value to a range so that we can interpret it. So whether 300 meaning, is it 80%? No. Or 70%? No, you do not know. And if you use such a squashing function like sigmoid, the 300 will come back to a specific number between 0 and 1. Say it may come to 0.55. Then you can interpret it as 55%. So that is how such functions are decided. There are a lot of such functions that you can use and work with, so which I'll be showing you in coming slides. But if you try to understand it closely, if you say that these are the weights for the respective inputs, then this is the dot product, which is 21.34, which is not so meaningful for interpreting. And hence, if you pass it to the function f, it will come back to a value between 0 and 1. Okay. So such squashing functions which help you bring the computed value of a neuron to a specific range are called as activation functions. Okay, activation is nothing but how much that particular neuron should be activated. So if I want to give an example, like if you if I say that if somebody touches you, so you will not feel that it is something irritated. Whereas if somebody hits you, it is kind of like irritation that happens. So the neuron, I mean, responsible for this output, whether it is a irritating feeling, or I mean something like what you can call it as, I don't know, I just say it as irritating. So if you want to call it as irritating, what should be the activation that should happen from that neuron? I'm just giving you an example that it is one neuron, but it is actually a collection of neurons that are responsible for this output. But if you assume it is a one neuron, then how much that neuron should be activated to decide that it is a irritating sense. So a touch is definitely not a irritating sense, and so the touch will have less weightage compared to um, the hitting. So hitting will have high weightage, and hence the activation function that I choose will should be synchronous to what I'm assuming here. Touch should be less activated, hitting should be highly activated, and so that decides how much the neuron should be activated. I mean, how much information or how much should be the strength of the information that is generated out of that neuron. Okay, but how much should be in a specific range? So it should not be something like 300 or 400 as we understood from the dot product, but it should be in a specific range so that you come to know that if it is 0.9, meaning it is very high, it's almost completely active. Whereas if it is 0.1, so you can say that it is not that active, it is just a simple output. So they are in the concept of neural networks and deep learning, we call such squashing functions, which bring the neurons computation into a specific range as activation functions. So these activation functions, essentially we try to use non-linear activation functions, meaning that it is not going to be just a linear function converting the summation into another value, but it is a non-linear curve. As you can see, this sigmoid is a non-linear curve. The behavior or the nature of this curve is not linear. It's not looking like a line, right? Basically. So when do you say the curve is linear? When you see the nature of the curve is something like a line. Okay, maybe this is a linear, whatever. Whenever you see the nature or the representation of your function as a line, then it is a linear function. And in neural networks, linear function will not make any difference. It is just like, for example, if you give x, I give you 2x, or I give you 0.5x. Okay, or I give you something multiplied or divided by x, or something added to x. So this is a simple linear function that is not going to help, and that is not going to help in the sense that it's not going to um, you know explain the complicated operation that is involved in the that is required to interpret the input samples. So I think this will be even more clear if I take you through the further slides, but just understand that we try to use nonlinear functions in the neural network. Okay. So as an example, you can see this is also non-linear, but it is linear, piecewise linear, correct? This is also piecewise linear, but as a whole, it is also a non-linear. This is tan sigmoid. So the sigmoid function applied on the, I mean, tan applied on the sigmoid function. So this is log sigmoid, and this is radial basis function. So all these are non-linear functions. Probably you might be aware of these functions being used as kernels in the concept of support vector machines, for example. So support vector machines, the simple or the naive support vector machine is a uses a linear kernel, meaning the data will not be transformed into a different space. Whereas if you try to use a specific nonlinear kernel, then the data will get transformed first, and then the computation happens in the transformed space. That's called as kernelization in the support vector machine concept, wherein you might have observed the usage of radial bases and such other activation of the kernels. So the kernels here are called as activation functions. Okay. So linear functions, because they cannot give you the interpretation of the data, or it cannot help you in understanding the data in a better way, because it will not transform the data into different spaces. And just it's just basically some other form of your input data. It is proportional to the input always if it is linear. Okay. So I'll come back to the activation functions, the specific activation function which is most popular in our coming discussions. So before proceeding further, let us try to build a neural network and see how the neural network can be trained for our problem. Okay. So as you have understood the working of a single neuron in the neural network, the same is applicable for each of the neurons set up here. So how do you build a neural network? Basically, you have to decide how many neurons you should be having in the input layer and how many these neurons you should be having in the output layer. And this hidden layer is your choice. You can decide to have any number of neurons. So if you increase the number of neurons in the hidden layer, your computational requirement will increase. So depending on how much is your computational power, you can limit it, and depending on what is the complexity of your problem. Okay, some simple problems may work with 3 neurons in the hidden layer or 2 neurons in the hidden layer, but some complicated problems require a lot of neurons in the hidden layer. So let us assume this hypothetical example wherein we have um, a classification problem, okay, with 2 classes 0 1 or yes or no. You can map it to anything, wherein I have the samples. So each row you take it as one sample converted into a feature vector. Assume you have extracted certain features out of your sample. So 1.4, 2.7, 1.9 is the first sample. And you know that because you have collected this sample, you know that it is class 0. Similarly, it is class 0, it is class 1, it is class 0. I want to use this data to train my neural network. And how did I decide this input layer as 3? Because my number of features is equal to 3. So your feature vector has dimension 3, and hence the input layer number of neurons is 3. And output, why I kept it as 1? Because I just want it as either 0 or 1. So I want this neuron to emit 1 if it thinks that the input vector falls into class 1. It should emit 0 if it thinks the input vector that I pass is belonging to class 0. Okay. So that's how you decided the input and output. And just for the sake of understanding, I have kept it as 3. So it depends on your application. Okay. Let's try to train this neural network to learn these vectors, how to map these vectors to 0 and 1 respectively. Okay. So what is required? You know, you have extracted the features. That is how the feature vectors are decided. So you know the inputs now. And you, because you have extracted the feature vectors and the data collection you have done, and you know what is the class of each sample, and you know the expected output for each input feature vector. But what is not known here, the weights that you should have in the edges connecting the neurons. So let's try to initialize this with random weights. Okay. And let's present a training pattern. So let's present this sample belonging to class 0, that is having 1.4, 2.7 and 1.9. And with the random weights that you initialize, assume it generates 0.8. Okay. How did it generated 0.8? You have initialized some random weights here, something like 0.3, 0.1, some random weights and some random weights here also. So what it does, it takes this 1.4, multiplies with this random weight that you have set, and computes the dot product. And you might have kept some squashing function like a sigmoid or any other function which generated some value, and there could be some random weight again sitting here. So that value and the random weight multiplied together is used here. Similarly, the others will also do the same process, and ultimately this neuron takes the output from here, weight from here, output from here, weight from here. Okay. And output from here and weight from here, does the summation and does the squashing, and that's how it generated 0.8. Understood why the 0.8 has come? So as an example, but what you were expecting is 0. So you wanted to generate 0 out of this neuron when you present this sample as input. But what it generated is 0.8. So what is going wrong? You know these features are good, hopefully, because you have done the feature extraction well, being an expert in that domain. And you know that 0 is the class of it, but your network is producing 0.8. So the reason is the weights that you have initialized are purely random, and the random weights are not so good. And I want to now adjust the weights so that this 0.8 goes to 0. Which all weights you should adjust? You should adjust these 3 weights here and these 9 weights here, correct? Let's see. So You try to adjust the weight here so that this value reduces from 0.8 to 0. Adjust the weight here, adjust the weight here, adjust the weight everywhere. So this weight adjustment is called as the back propagation, wherein what you have computed here is the error, which is the difference between expected or the actual output and obtained output. So actual output and obtained output is what is the error, and that error you want to use as a deciding factor or a factor to adjust the weights. So you try to uh, update the weights with respect to the error that is produced. So go on using the error to adjust the weights, and hence you adjust the weights till your network produces 0 as the output. Okay, for this particular sample. And now once you find that the weights that you have adjusted is uh, is proper to generate 0 as the output for this input vector. Fine, you have trained the network for this particular sample. Next, go with the second sample, right? You are expecting 1 here, but it is probably producing 0.9, and hence you want to adjust it again because there is an error of minus 0.1. So again, you adjust the weights of the edges to convert the network to produce 1 for this particular sample. So you go on doing so until you see that your network is producing appropriate outputs for each of the feature vectors. Why you need to repeat it multiple times is because when you adjusted the weight for this particular sample to generate 0, then when you move to adjust the weight of the network again to make this sample leading to 1, then the weights are modified, correct? And the modified weights may not be still good to produce 0 for this, right? Initially it was random, then you adjusted to generate 0 for this sample, then you adjust it to generate 0 for this sample, then you are not sure whether the adjusted weights are still good enough to generate 0 for the earlier sample. So that will happen for every new sample. When you do the adjusting, the previously adjusted samples may not still work well or may work the weights. Okay, depends. So then what you do, you pass through all the samples one by one and try to adjust one by one. Once you complete all the training samples, again you come back and do a second pass and see and try to adjust again. So you do this several times. Pass the samples, adjust the weights, and again go back, pass the samples, adjust the weights, pass the samples, adjust the weights. So one fine iteration after maybe several thousands of iterations, the weight that gets adjusted will be the final weights which will generate the expected output for every sample. Okay, so you repeat this thousands, maybe millions of time, each time taking a random training instance and making slight weight adjustments. And algorithms for weight adjustments are designed to make the changes that will reduce the error. So basically, your goal is to see that every training sample is learned from your network, meaning that whenever you post the training sample, you expect 0 to be produced or 1 to be produced based on what you have set in the training data. So after several pass, it may come out with some weights which are adjusted with several adjustments that will fit for all the training samples. And that will, when I say fit, meaning when you pass the training sample, it generates the corresponding output. Or in a holistic sense, you try to look at from a complete training set perspective that you compute the overall error. So if you have 100 samples, out of which if you compute the loss or the error for every sample and sum up the error and average it by the number of samples, say the total error is something like 55 and divided by, say, if there are 100 samples, so 55 by 100 is, say, close to 0.5. So something like that. Okay, so the overall error is 0.5. So if whether this 0.5 average error is acceptable for you, if it is acceptable, then you can stop. If it is not, you still have to continue till you get a specific set of weights for all the edges, which will reduce the overall average error to a smallest possible number acceptable for your application. So you want to say that the average error of these training set from my network should be less than 0.05. So until you reach that 0.05 average error or the overall error, you want to do the training. What is training? You pass the sample, maybe instead of choosing one after the other every time, you choose random samples and just pass it, adjust the weight, and see that it is working. So this is called as neural network training. And definitely you feel that it is very boring and it is very simple, or you can say that it is completely blind. Correct? There is no intelligence involved, but that is how your brain will also learn. Every time you pose a sample, it adjusts the weights, and finally one day after it has seen good number of samples and adjusted the weights, and the weights are so rich after some several iterations, the weights are so rich that whenever you pose the samples, it will perform the expected action, and also that it will generalize it in such a way that the weights are now applicable not only to your training set but also to the samples which are not shown to the network. So that is the generalization you want to achieve. Okay, not only your network should fit to your training data, but also it should try to generalize to unseen samples from the knowledge that it has gained across. So overall, what is needed? You know the input, meaning you know what is going in, and you know the output, meaning what you know what is expected out of the network, and what is the deciding things, the number of neurons in the hidden layer, and the weights of each edge. These are the learning factors. But anyway, you fix these neurons in the hidden layer, but you try to iterate through several times to adjust these weights. That is the training. Okay. So if you look at from a decision boundary perspective, because we are assuming two class problem here, assume the red circles are falling into one class and the yellow are falling into other class. What you want to do is basically you want to bring out a curve. So definitely it is not a linearly separable uh, problem, correct? So you cannot keep a line which can separate the two classes, right? You cannot think of it line here. So if you try to keep a line, definitely it will not be 100% accurate. It will have some errors. Say for example, if I keep a line here, right? So if you say that the samples above the line are yellow class and sample below the line are red class, then you will have misclassifications for these samples and for these samples also. And hence, this problem is definitely not linearly separable, meaning a line cannot be fit to separate these two classes. What you have to do is you have to fit a curve. You have to fit a curve which comes like this and goes all the way here and probably takes you through this. And the weights in the neural network will try to adjust this curve. So what you see here is there is a non-linear transformation happening from your input data to the output vector, and that non-linear transformation is nothing but the non-linear decision boundary that's being built. So this is the reason why I told you the squashing function that we use in the neuron should not be a linear function. If it is a linear function, then what the network tries to do is tries to put a line. Okay, whereas this problem is not linearly separable, and hence the nonlinear separable kind of problems require a nonlinear squashing function which will convert the input value into a transformed value in a nonlinear sense, and hence the nonlinear transformation functions are useful. But what is decided, what need to be decided is the weight that should go in. So that weight will adjust this nonlinear curve. So in the initial random weights, your nonlinear curve might look like this, and hence your error will be very high. So some of the samples will get properly classified. Some of them will not get classified, and if you compute the overall error, it may be very high. See, in this curve, the error is very high. So next you adjust the weights, right? There is still error. You adjust the weights. There is still error. You adjust the weights. So as you go on passing the samples again and again, across several forward passes and backward weight adjustment, your curve will become eventually so complicated and built in such a way that it is 100% fit to your training data, and whatever samples above the curve are into one class and the samples below the curve are into another class. Hope you are able to see this. So this is the target of your neural network weight adjustment. Okay. And here you may ask me that this is so complicated curve. If any new sample comes in and if it is a yellow sample but placed here, definitely will be misclassified, and hence you don't train your network so heavily that it will give you 100% accuracy, or you can call it as 0% error for your training data. But the 0% error in the training data may lead to a curve which is overfitting. So you know the problem of overfitting and underfitting, right, in machine learning. So overfitting is where your your algorithm is fitted to your problem 100%, so complicated, but the complicated nature of the curve making it so less effective that any new coming samples which are close to the curve are having the chances of misclassification. So try to keep a buffer, something like do not be so stringent to expect 100% accuracy or 0% error in the training of neural network. Keep a range. So if it is 0.1, meaning if it gets you 99% of the samples properly classified, maybe it's a good point for you to stop. So you being the experts of that domain and the problem, the complicated the level of complexity that the problem has. Based on that, you keep a threshold for the error, the training error, and stop when you reach that threshold. Okay, and hence you will have a good generalization. So if you just want to bring this sample in below this curve and try to adjust the weight so that the curve goes like this, then there will be a chances of error for the unseen samples. Instead, if this sample is going wrong in your training, let it be. Even with that, the generalization will be very good. Okay, so that is what you need to understand here. So with this, what we have understood is the weight learning algorithms for neural networks are very dumb. There is no standard algorithm involved as of now, as you understood. It is just the adjustment by using the error that is produced. You try to adjust it the weight, and they work by making thousands and thousands of tiny adjustments. So depending on how big your network is, right? If just a 3 into 3 has 9 weights to be adjusted plus 3, so 12 weights. So if you increase this to 1000 neurons, and definitely your input feature vectors will not be so simple that they are only 3-dimensional. You may expect 100-dimensional feature vector or some 1000-dimensional feature vector also. So assume a feature vector having 1000 dimensions and a hidden layer having 500 neurons. It is 1000 into 500, so which is a very big number, right? So many weights you need to adjust. And why the neural network will be so effective and if at the same time generalizable is the decision is not dependent on only one neuron or only one weight. If your network is having 1000 input neurons and say 500 hidden neurons, then there are 1000 into 500 edges. Each edge is having its own responsibility, its own weight. So the decision is distributed across the edges, across the weights, and hence each weight is making its tiny contribution to the final output. And if one weight is going wrong, probably it will not hamper the decision of your network, because it is not the one neuron that is responsible or the one weight that is responsible for the final decision. So They work by making thousands and thousands of tiny adjustments, each making the network to do better at the most recent pattern, but perhaps a little worse on many others. But by dumb luck, you can just say eventually this tends to be a good enough to learn effective classifiers for many real applications. You just see this. If your network, after several weight adjustments, if your network tries to establish this complex curve establishment is never possible in any of your conventional machine learning techniques. So if you see SVM with kernel, so SVM with kernel, whatever kernel you put will be not so good in bringing up such a complicated curve to separate the two classes of your interest, but neural network will bring in, because it is not a kernel that you have defined only one, it is the several kernels that will come together to form this complicated decision boundary. So that is the reason why neural networks are uh, adopted to any application, any complicated application. With this simple weight adjustment concept, they get adopted to any complicated problem. So weight adjustment is the crux of your neural network training. But what is important again is the how do you adjust the weight? So with what? So you adjust the weight in a very well structured way. It is not that you randomly select a weight and try to adjust it. No, you go it in a very uh, very much defined way. As you forwarded your input sample all the way from input layer to the output layer, you try to adjust the weight all the way back from the output layer to input layer. Okay, so that is the reason why it is called as back propagation. So the network training has two things essentially. One is forward propagation or forward pass, wherein you pass the input feature vector that gets passed across all the neurons, and computation happens and it reaches to the final neuron. And final neuron, you have kept your expected output, you compute the loss based loss or error. Based on the error, now you propagate back from lost layer, that is the output layer, all the way back to the input layer. And during your back propagation, you try to adjust the weight, okay, with respect to the error that has occurred. And this process of adjusting the weight from last layer till the first layer, right, by looking at the error that is produced, is called as back propagation. Okay, so a set of examples for training the network is assembled. The input data is entered into the network via the input layer. Each neuron in the network processes the input data with the resultant values steadily percolating through the network layer by layer until a result is generated by the output layer. So this is forward pass. Now the actual output of the network is compared to the expected output. So what the network has produced versus what the user is expecting, that will result in a error or the loss. And the connection weights in the network are gradually adjusted, working backwards from the output layer through the hidden layer and to the input layer until the correct output is produced. Okay, so fine tuning the weights in this way has effect of teaching the network how to produce the correct output for a particular input. That is how the network learns. So you're trying to make the network learn by the error that is it has committed. Okay, so there is a rule that we keep in the weight adjustment that is called as the learning rule. So if you now see from this single neuron perspective, you pass in the input. Okay, so there is an activation function that is kept, which uses this dot product and does the uh, activation or nonlinear mapping of that dot product and generates the output. But this output is different from what you are desired, or the what is your expected output is. So you compute the error. So this A is the actual and D is the desired. So A minus D is the error, and you wish to adjust the weights of the different edges based on this error. And this rule called as delta rule is used to adjust the weight. So there is a W's, which are the weights. You want to adjust each W. So the weight will get updated with this factor now. So the weight will get updated with a portion of the or a proportion or a factor of the error that is generated. So as you can see, if this is the weight that was present during the forward pass, and if A minus D is the error, so I decide a you know a factor of this error to be used to be added to this weight, so that this weight gets updated, and I use that updated weight as new weight. And this n, the factor, is called as learning rate. So if you want to give so much of weight update in one go, then this n will be big, and you feel that having a bigger proportion used for the weight adjustment, if it might lead to a local minima. There's a concept of local minima or local uh, maximum. So you just want to escape from them, and that is the reason the weight adjustment will not be the complete error. It is just a small proportion of the error, and that is tunable again. So you want to train this n also, or sometimes you try to start with a smaller value of n, the learning rate. So the weight gets updated, and the updated weight is used again to perform this. So this will be repeated as long as the output is very close to the desired output. So when a neural network is initially presented with a pattern, it makes a random guess as to what it might be. It then sees how far its answer was from the actual one and makes an appropriate adjustment to its connection. So make a random prediction, then see, okay, my random prediction is close to the desired. If not, okay, how far am I from the expected output? So try to adjust my decision factors, that are the weights, so that I reach to the desired output. So that's the learning rule of a neural network. Okay. So now, with this understanding of how the neural network gets trained, if I try to show you the different characteristics of this such a neural network, it is learning from experience, right? So any complex problems that you have in your hand, but if you have sufficient data, so what is required is you should have sufficient examples to show the network that, hey, see, for the earlier sample you may be doing good, but for this sample you are not doing good, meaning that you are not generalized well. So as many samples you pose, so much will be the learning that your network happens, and it is trying to learn from its experience of seeing several samples. So that is the reason why neural networks can be used only in such cases where you have plenty of training data in your hand. So as big as your training set, so big will be your effectiveness, or the the neural network's adaptability chances. So if you have some, say for example, a two-class problem with say only say a simple number like 50 samples from each class, chances that your neural network adopts to those 50 samples problem is very less. Okay, so if you have good amount of samples, then the chances will also increase proportionately. Okay, so your neural networks are data hungry. Okay, so generalizing from examples. So if you pose lot of samples, it tries to understand each and every sample and the relation of that sample to other sample. Say for the class 1 itself, you have posed 1000 samples. So it has to say all those 1000 samples are from class 1, correct? Definitely it cannot remember. For every sample, if it tries to keep one weight, then it has to keep 1000 different weights for one edge. That's not possible. You are expecting one weight for one edge to be working or to be effective for all the 1000 samples. So it is now trying to relate the 1000 samples, how they are called as a single group, why all those 1000 samples should fall into one particular group. So such a relationship will be learnt by your network, and in that journey it will generalize so that it can work for unseen samples also, because it has understood the data. It has not uh, you know what you can call it as, it is not remembering your data, right? It is not storing your samples. Instead, it is storing the relationship, the concept of the sample, and hence it will work for unseen sample. So rapid application development. neural networks are generic machines and quite independent from domain knowledge. Say, do you see any domain knowledge is required here in training neural network? Anybody who is given with data with extracted features, and if I ask him to build a classification problem with just understanding of how to construct this neural network, I mean how many input neurons decided based on the number of features in the input vectors, and how many output neurons decided based on how many classes are there in the problem, and in the hidden layer he can do some trial and error to fix the hidden layer, and just goes on training. And today you have a lot of tools wherein which you do not have to do anything. You just have to pass your data and give some simple configuration of the network. This is the input layer, this is the output layer, and this hidden layer I want some 10 neurons in the hidden layer. And those tools, I mean the libraries, are built for training the network and updating the weights till the network learns to produce some error with some like a threshold. Like you expect the network to be trained until the error is 0.01. So you would set that. So anybody can set it and start training that. If it's possible, it get trained and he will have a network for your. I mean, he has a solution for his problem. So it is not expecting any such great domain knowledge to be required to build neural networks. Correct. Adaptability to changing environment. So because it is learning from its experience, it can be easily adaptable. It is computational efficient. So only thing is the training requires a lot of computation power. Whereas once you have trained a network, but using it in the actual prediction environment and in the real usages, like you deploy it to some place where the classification is required, you have trained it. So you just went and rented some computing power. You trained your network. So you now bring back the trained network. What is your trained network? It is just that it is 3-layer input, output, and hidden. And so each layer is connected enough with all the neurons, and each connection has a weight. So that weight is what is trained from your training process. Now the prediction or the actual testing or actual the usage is you pass a unknown sample that goes from input layer all the way to the output layer by using the trained weights, right? And in the output layer, whatever output comes out, so if it comes out as zero 0.9, say you say that the probability of class 1 is high, so you classify it as 1. You keep that simple final decision criteria at the end. So one pass is very simple, right? It just that it is a simple summation followed by squashing. There are, say, if you have 1,000 neurons in the hidden layer, it is 1,000 summation and squashing followed by one simple summation and squashing in the last neuron, the output layer neuron. So 1,000 plus 1, 1,001. 1,001 simple dot product and squashing are taken place. So if you have a simple personal computer also, you can deploy this neural network. So it is computationally efficient in the prediction mode. Maybe training requires a lot of computation. And it has non-linearity. So what we try to achieve in the real world is how to address these non-linearly separable problems. So it requires a lot of domain knowledge in case of conventional machine learning. For example, in the case of SVM, if you try to build a SVM for nonlinear separable kind of examples, then you might have to know what are the different nonlinear kernels ranging from RBF, radial basis function, or a simple polynomial. So you should know all of them, correct? What is each and how the working is. So such a strong experience and expertise is required to achieve nonlinearity. But here, nonlinearity is achieved through its simple adjustments. So that is the characteristics of neural network, and the accuracy of such a neural network depends on the training set. As I said, if you have a good amount of training samples, then automatically the training will be efficient. I mean, training will be successful. And the features. So this is most important because what you're adjusting is the weights, but what is fixed is the features. So if someone is working with a fixed set of features, and the features, if he has extracted and he's not from the domain, if he is not expert in deciding what the features are, then again your training may suffer. See, if the features themselves are not the good representative of the data, then the network cannot learn it, right? So the features are very important. And the network structure or learning algorithm, basically what should be the squashing function, and how many neurons, right? So such things should also be decided. So these are all the deciding factors for the accuracy of the neural network. Okay. So that is about the neural network so far. If you have any queries on what exactly the neural networks are, you can ask me. Otherwise, we can stop for uh, break and we'll gather back for deep learning.
Sir, are only dendrites the receptors of signals, or can axons or axonites can also receive the signals from other neurons?
Sorry, madam, your voice is not so clear. Can you put it on the chat?
Yeah, yeah, sure.
Yeah, if anybody else has any query, probably we can discuss.
Sir, I have a small doubt in this.
Yes,
Hello?
yes, please.
Sir, actually, when we're going for 100 rows and some 20 columns, right? So, when we run these data set into machine learning, models and the classifiers and all, if I
Okay.
get around the 96 or to 98, which I decide what should be the accuracy and all. Is it necessary that again should I try neural networks? Uh, is it like logic goes like that, sir? If it stops with 98%, which I decided that is okay, should I again try this neural network or not? Will you please explain, sir?
So first of all, it depends. So what you said, 98. If it is your training accuracy on the training set, if your network or if your the model that you have built, maybe any machine learning model, if the training accuracy, I mean,
Sir,
if
actually,
you
I'm speaking about model accuracy, sir. I'm speaking about
model
model accuracy.
accuracy
Yes.
on the test validation set or the training set, on which set you're
On
talking?
test data, sir. On test
The
data set.
test data, right? So 98 on the test data is really good. And if your test data is a good representative of your actual data, meaning if your test data is having all possible, mm, you know, uh, what I can call it as all possible complicated and easier and different types of samples. If it is a good test set, basically what I'm calling it as. So if it is a good test set and if you are achieving 98 with a good test set, then that is really commendable and you can stop there. Depending on what the application is. See, somewhere if it is a application pertaining to a very accuracy demanding problem, say you are deploying this in the defense, in the security. So 98 is still a low number in the security or defense related applications. Like out of 100 people, you are properly classifying 98 persons, and for the two, your classification model may go wrong. And what if those two are the kind of like, if I just give an example, if those two are the terrorists, or if those two are breaching the security, and if your model is going wrong with them itself, then it is not good. So sometimes we may be expecting 99.99 for such a severe applications. But if our application is not that severe, then 98 is also a good number. So the number 98 or 90 or 70 depends on what the application is. So that probably you have to decide. But in general, in most of the cases, achieving 98 for any problem is really good effort. But I think that is sufficient, and only a few of the cases require more than 99 maybe. Nowadays we see that something like people are trying to build this, whether the person is affected by COVID or not, through the chest X-ray or the what do you call it as other type of scanning images. So, and they try to claim that they have built a model which is achieving 98. So, but even a model which has 98 in such things is not going to be deployable, because 2% error is like at the cost of 2% of the people. It is. So 2%, if I multiply
Of
like,
course, sir, I do agree with
yeah,
you. But there, see, COVID is much complicated. Even doctors are not able to diagnose it
correct, correct.
to 100. But how the system can do, we can't expect that.
Yeah. So it
Basically,
can
this even
be
people with
a
lung cancer,
synthetic.
people with lung cancer are having a diversity of nodules inside their lungs.
True, true,
So
true.
again, that will make some noise. Okay, that is okay. That is different thing. What I'm asking is whether if I get a consistent accuracy with machine learning, again, should I try with neural networks or not? That is my question. If I'm getting
Not,
what are
not
needed in machine
necessary.
learning, this thing,
Not
and
necessary.
can I go
If you are
directly to
achieving,
neural networks without using that ML? Is it true?
see, not necessary.
Okay.
That every problem should go to neural network,
Okay.
and the problems wherein you find it difficult to decide what should be the features, or
Okay.
probably you have tried out with all known feature extraction techniques. I
Mhm.
mean, all the known classifiers, and they are not fitting well. And there is something like you want to build a classifier, like a support vector machine is not possible. You want to redefine the classifier itself. Then that's where your neural network might help. Neural network is a framework which builds a classifier basically based on your data. It comes up with a classifier, whereas a SVM by itself is a classifier. So neural network is a very generic concept which can bring up a new classifier of its own, as you saw from the decision boundary that I generated. So the decision boundary is the classifier. Whatever that curve you see, that itself is a classifier. So for any data that you pose, if there is enough samples, a classifier will be built by the network. So you can go to neural network at the end if you cannot achieve what you're expecting from the other machine learning techniques. But on the other way around, the conventional machine learning techniques are, not so computationally expensive to build and productionize. I mean, they do not require a lot of data. So it all depends. So if you can push huge amount of data, then you can go to neural network. If you do not have a sufficient accuracy in conventional learning, then you can go to network. So that's the decision factors.
Thank you, sir.
Yep. So, madam, to your question, can only dendrites be the receptors, or can axons also receive Y signals from other neurons? Okay.
Yes.
So, yeah. So coming back to this question, right? So here there are a lot of things in the actual biological neural network which may be taken as inputs into the neuron, which may be deciding the outputs. But when we move out of biological neural network, we're trying to imitate it in the artificial neural
What
network.
second
We
thing
have
will come?
considered there is a background noise. Somebody can mute, please. So somebody's on. Somebody's on mute. Please mute yourself. Hello. Yep. So basically, in the artificial neural networks, we have taken only these dendrites, and dendrites, the connecting synapse. So the synapse are the
Okay,
genetic
बात होती
proteins.
है then
Dendrites are connecting them.
और इस सबको क्या बोला जाता है?
Fine then. So probably if you have any other question, you can just post it in the chat, and later when I come back to the next session, I'll discuss them and go further.
Analysis
So
और
let's have a
requirement
break
के बीच
for
में फीड होती
30
है
minutes,
क्या होती है?
Yes,
and
sir.
we'll gather back again at 12 p.m.
We'll have a break now up to 12 o'clock. 12 o'clock sharply, we will start the next session.
Sure, sure.
So, sir. Participants, don't leave. I have to talk regarding the attendance. We have a confusion about the some of the names while
Feasibility study
calculating the
सुना है कि
attendance.
नहीं सुना है?
Some of
सुना है
you,
ना? क्या होता है उसका?
all of you unmute. Vishal Gupta, please unmute. Vishal Gupta, where is? Some of the names are not understanding. People are joining with the different names and shortcuts. One name is like ECE NAC. Some person joined like this. We don't know the name of this person, actual registered name. Anybody is there? ECE NAC, like that name came. There now. I just a minute, I will check it. Where now is not online. Is there? Here it is there. Now it is online. Who is this ECE NAC? Not responding. So we will not count it attendance. If you people are not responding, whoever joined with ECE NAC, he has to respond. Then only we know your registered name. Another name GVGK is also online now. GVGK. Another name Jaya. She is also online now. And next Sujesh. Sujesh is also is not there. She or he is not there. I think. There na. Sujesh also there. And another one UMA Bala. Bala also there. Sujesh, what is your registered name? Sujesh, please unmute and say. If you people not respond, we will not count it as an attendance. And UMA Bala also. These 5 members, there is ambiguity counting the attendance. So we announce there is no response from your side, so we will not count it. So all of you please join with your registered name, then only it is possible to calculate the attendance easily without any problems. And if anybody is joining with a different name other than the registered name also, please inform to us. So we will update. Sujesh only. It is a registered name. Sujesh is the registered name.
Yes, sir.
It is there now. Sujesh only. Like that, it is there. Maybe you joined, you registered with a different name. What is your complete name, registration name?
Sujesh HK.
What is that, Sudesh?
HK.
HK na. Sujesh HK. Is there? Note it somewhere. Sujesh HK. And others also. Uma Bala. Are you there? Uma Bala. And later you don't call and ask we are attended and not given attendance like that. Whatever the names I announced, these 5 people have to respond. Then only they will get the attendance. One name, tell the name again. GVGK and what's name? ECE NAC. GVGK. Next Jaya. Uma Bala. Sujesh HK. Sujesh HK, no problem. Huh? Check it once. Sujesh HK. Okay. Thank you, all the participants. We'll come back and we'll start the next session in, at 12 o'clock sharply. Okay. Thank you all.